Gente, bom dia a todos. Vamos começar mais um colóquio do Instituto de Física de São Carlos. Hoje, para apresentar o nosso palestrante, eu convido a professora Cibele para fazer as honras da casa. Obrigado.
Bom dia. Eu agradeço ao Instituto por receber o professor Carl Winning. Ele é bacharel em astronomia pela Ohio State University em 1976. Obteve mestrado sobre educação em planetários na Michigan State University em 78 e doutorado em educação na Illinois State University em 2007. Winning foi para a Illinois State University em 78 como diretor do planetário e durante 22 anos de serviço nesse cargo recebeu cerca de 250 mil estudantes do ensino fundamental, médio e membros da comunidade no planetário. Entre 94 e 2008, ele transformou o antigo sistema de formação de professores de física, que tinha apenas 5 estudantes na licenciatura, né, em um programa reconhecido de nível nacional que está entre os maiores do seu país. E a Illinois State University formou cerca de 15% dos professores de física do ensino médio que atuam no estado de Illinois. Ele também atua como consultor internacional e tem dado palestras, convidadas, seminários e workshops em muitos países, como, por exemplo, Rússia, Chile, México e Indonésia. Ele, ao longo de sua carreira, ele teve vários reconhecimentos como formador de professores. Atualmente ele é aposentado, mas continua atuando junto ao Departamento de Física da Illinois State University. So, thank you very much for visiting us.
Testing, 1, 2, 3. Good, it works. Good morning. I'm delighted to be here. Again, I'm Carl Winning from Illinois State University. And today I wanted to talk a little bit about something that we're using at Illinois State University. It's a new model of physics teaching, which we believe has broad applicability to other science teaching methods, such as chemistry and biology, environmental science, earth and space science. I want to talk about the program today and how it has affected our teacher education program at our university. But first, let me say a little bit about science teaching, a wee bit about the historical background. I'm not a research scientist. I'm a teacher. I'm a teacher of teachers. One of the things that I do is I like to read the literature. And over the years, I've studied many of these individuals on this list. John Dewey, you'll probably recognize the name, University of Chicago. That's very close to my university. John Dewey's friend was Charles DeGarmo. Charles DeGarmo was a member of our university, and Charles DeGarmo influenced education at our university. And one of the ideas behind John Dewey's work is that students should have what he called experiential learning. They should learn, they should develop knowledge on the basis of experience. That is something I firmly believe, and now more than 100 years out, I think that we've learned a new way of helping our teacher candidates teach science so they know what inquiry really is. So these are many philosophers, and many have wonderful contributions to science teaching and teaching in general. But in my opinion, none of these, not even John Dewey, not even Brunner, Jerome Brunner, not even Carl Rogers, none of these people, as far as I'm concerned, has developed an appropriate explanation for how we should teach science. And as this program ends today, what I'm going to do is explain where this method came from It was developed at Illinois State on the basis of a very interesting experience that happened in the spring of 2004. But let's take a look at definitions of inquiry. In the United States, we refer to national standards all the time. One of the publications that came out several years ago, the National Science Education Standards, which in fact have been replaced recently by the Next Generation Science Standards, says essentially this about inquiry. Inquiry refers to diverse ways in which scientists study the natural world, or activities of students in which they develop knowledge. That publication does not go on to explain how one learns using inquiry-oriented approaches. If you tell doing science is what scientists do, well, what kind of an explanation is that? Our teacher candidates, though they are physics majors, they're not scientists. If you take a look at the National Science Teachers Association, they say students learn to ask questions and use evidence to answer them. Well, that's fine, but how do you do that as a teacher? Students learn to conduct an investigation. Using what? The old scientific method? We know there's no universal scientific method that will help us to solve every problem in physics. That's a myth. That's mythological. So we have to really answer for ourselves. That is, teacher educators have to answer for ourselves this question. What is inquiry? What is inquiry-oriented teaching? We need to clearly define it, and we have to define it in a way that we can teach others how to use inquiry-oriented teaching in their own classrooms. Now, if you take a look at the general science education research literature, you can really argue that there are four major themes in appropriate education. This is in general. We say that our teaching should be student-centered. I agree. What we are seeing here today is not student-centered instruction. This is instructor-centered instruction. I'm up here giving a lecture. Now, I've been teaching physics for 37 years at the university level and also at the high school level. I'm a certified high school physics teacher with experience in high school, and as soon as I get back to Illinois, where I teach, I have to teach a physics course at the university, and I also teach a high school class. I'm teaching high school still after all these years. And I always try to make my courses student-centered, especially my high school courses. So student-centered is that we put the attention on the student, that the students do the work of learning. We often confuse teaching with learning. We assume that if we teach, students will learn. Anybody who's taught a science course knows that that's not the case. The real work in the classroom is the work of the students. Students have to learn. Students will sometimes learn even if they have a poor teacher. Sometimes students will learn if they have a good teacher, and they'll learn more. But learning is what students do, and we have to focus on student learning. As a new teacher, I often hear the question, how well am I doing? But you know that you've become more of a professional when you start asking the question, how well are my students learning? That is the job of the teacher, to help students learn. Our teaching should be knowledge-centered. Now, I did a little bit of a discussion last night with a group of students, and I asked them if the earth actually spins around and around. And they said yes. Yes, the earth rotates. I said, how do you know? And they were kind of surprised by that question. They said, well, how do you know the earth spins? And the answer came, well, I read it in a book. Or my teacher told me. That's not science teaching. Because we're not helping the students gather knowledge. We're helping them gather information, facts, beliefs. You might, as a teacher, say, look, it says right here in the textbook, the earth spins on its axis. But if we teach solely on the basis of a textbook, or any kind of book, we're teaching religion, or maybe we're teaching history, but we're certainly not teaching science. If I ask you to define science, I think we could generally agree that science is both a combination of content knowledge and the processes used to obtain that knowledge. That is, knowledge is an evidence-based belief. And unless we provide the students the knowledge and allow them to produce their own understanding, they don't have knowledge, they merely have belief. So the other thing that we should do as teachers is have an assessment-centered classroom. These are classrooms in which I, as a teacher, constantly listen to students. There should be a two-way conversation in a classroom all the time. I want to know what you think, and you think, and you think. In my own teaching, I use a process called whiteboarding. And a whiteboard is a large panel upon which students will write. And then they take that to the front of the classroom, and we discuss what the students have done. And this way, when they tell me about their information on the whiteboard, I, as a teacher, can learn what they're thinking. And many times I find out that they have these wrong ideas or misunderstandings, or they're just simply doing something wrong. Now, another thing that I do in my classroom teaching is to maintain a community-centered classroom. I'm one teacher. In my country, you might have 20 to 25 students in a classroom. Here, I'm told, 30 to 40 students is not uncommon. That's one teacher, 40 students. That's a terrible student-teacher ratio. So what we should do as teachers is to multiply ourselves. We should let the best students in a class become teachers as well. You all have had this experience where there are some students, everything, they know it immediately. They are very, very smart. They're deeply insightful. Well, why not use those to assist with your teaching? I often break my classroom into groups of 3 students, and give them different types of activities and make them work together. And a lot of times I will control who's in each group. So I always try to make sure that my groups have a range of abilities from very gifted students to maybe not so gifted students. But in so doing, I multiply myself, and the students can learn much better from having direct access to a teacher, even though that teacher might be a fellow student. Now, we can ask about the process skills that we should be teaching in relation to science, and I feel that even these are rather vague, unclear. Oh, we know what this means, okay? Asking questions, developing and using models, planning and carrying out investigations. That's fine. But if our students who are graduating from our universities have been sitting in a college classroom for 4 years, and they have been in classrooms which are teacher-centered, they are not community-centered, they are not assessment-centered, they are not knowledge-centered, then how can we expect those teachers to go out into the high schools of this country or any country and to teach in a brand new way? Linda Darling-Hammond is a very known education researcher in the United States. And she's made a point of saying, teachers teach the way they themselves have been taught. So if you've been taught physics by saying, watch a demonstration, read the textbook, listen to a lecture, do a laboratory exercise where you're told to follow the instructions 1, 2, 3, 4, then what will happen is you will probably teach your high school class the same way. Teachers teach the way they themselves are taught. And so this stuff is so vague, it doesn't help me as a teacher educator to prepare my students for the life that they have chosen as teachers. So I would argue that there is a tremendous need for some sort of guidance. In 2004, I was desperately in need of this guidance myself. By that time, I had already been a teacher educator for 10 years, and I still was not certain about what inquiry-oriented teaching really meant, what it really looked like. Oh, I had some ideas, but it wasn't until I was confronted by one of my students who said, "You did not teach me how to do inquiry," that I finally started looking inward and asking, how does one learn to teach using inquiry? Now, again, these are some of the descriptions that I might give to traditional approaches of teaching. The teacher is seen as an authority. Students receive knowledge. And I put knowledge in quotes because it's a belief system. It's not knowledge. In many cases, the students do not have the evidence to support their belief. And many times, the emphasis is on equations and finding the right equation to find the answer to a mathematical exercise at the end of a textbook chapter. On the other hand, inquiry-oriented teachers are seen as facilitators. My most common response to students in a classroom is this: well, I don't know. I'm just the teacher. You're the scientist. You tell me. My students get to hate that. And after a while, they stop asking me for the answers because I won't give them the answers. They have to work it out. They have to figure it out themselves. Students are responsible for constructing knowledge on the basis of their own experiences. I place tremendous emphasis on knowledge and the epistemology of knowledge, how we know what we know, and on procedures. And I'm going to show you the techniques that I've learned. Now, before we go any further, there are two fundamental questions that I feel need to be asked. What is the goal of science teaching? I always ask my students that. What is the goal of science teaching? And in the end, I think the general consensus is we're looking for science literacy among our students. Now, what is science literacy? Well, one might argue there's many, many different types of science literacy depending on how you want to define them. But in some sense, I hope my students settle on a definition that includes a broad range of knowledge, scientific skills, and intellectual process skills, such as critical thinking and scientific reasoning, and hopefully the dispositions, their attitudes. Those are things that I try to keep in mind. Now the question is, how do we best teach these types of skills? The science skills, the intellectual process skills. Well, I propose an answer today called the levels of inquiry method, or the model of science teaching. Not quite a method yet, it's a model. So I want to talk about that today. Now, these are 6 different levels of inquiry. I start with something called discovery learning. Now, for those of you who are experienced teacher educators, you know that discovery learning is something that is done generally with young children, 5, 6, 8 years old. And you say, you do this with high school students? Hey, I do this with college students. Hypothetical explanations on the other end, really complicated. Do you know, have you ever asked your students questions like, you know about the buoyant force, right? The floatability? Floatabilidad? You know about that. Where does that force come from? Do you know the answer? Okay, a lot of us do. Okay, we're physicists and physics students. But a lot of us, I suspect, probably don't. Never really thought about it, maybe. So what we tried to do is get students to go through a range of discovery learning, interactive demonstrations, inquiry lessons, inquiry laboratories, real-world applications, and hypothetical explanations. This is the sequence of steps that I've developed starting in 2004 and continue to develop even today. Now, our friend Dr. Marcos over there. Marcos, raise your hand. He and I have had some very interesting discussions, and he loves Paulo Freire, okay? And so we had some discussions about Paulo, and even he provided me some additional insights to this method. And so before I left my hotel room yesterday, I was furiously writing things that I had learned from you because of discussion. There's so much we still can learn about this method. But one of the things that we have found that helps with this sequence is that we start on the left end and then with a given topic go through each of these levels of instruction until such times as the students develop a deep knowledge, a total comprehension of the subject matter. And I would love someday to come back and do a workshop on this here. But for now, I'm just going to have to leave you with a simple example today. This is all written up in the literature too. So, but we start on the left-hand side here with discovering learning. And there, it's not very sophisticated. Intellectual sophistication is not high. You can use this with first, second, and third grade children. Up there, on the other hand, hypothetical explanations, very complicated. I have students develop their own formulas and explanations for things, and then they have to predict and mathematically predict outcomes and then experimentally determine if they're correct. Then the locus of control changes too. That means who is in control. At the beginning here, in the discovery learning part, I'm in control, or the teacher's in control. Because remember, these are not scientists. You can't just simply tell them to go do science. They don't know how to do science in most cases. So by the time we get to the hypothetical explanation, the student is almost entirely in control. We might make a few suggestions and ask a question or two, but we give no advice. And this has worked quite successfully with our best students. Not all students get to that level. So let's take a look at discovery learning, the lowest level here. This is an area where we introduce subject matter. We give them a series of examples. The students develop a concept. Okay, science education research tells us concept first, term second. Don't introduce a term until students understand what it means. So the idea is to let these students see a variety of examples and then from that develop a concept. They have some sort of an idea, a mental construction. Oh, that's what that means. Oh, yes, yes, yes. How we do that, I'm not quite sure. I'm not sure anybody knows how we develop concepts. If I show you 5 or 6 or 7 different animals down here, and they all have long tails, and they're furry, and they have 4 legs, and they go, meow, meow, meow. Some might be yellow, some may be black, some could have stripes on them, some could be sleeping, some could be running. But in the end, you develop the concept. Oh, yes, I know that. I know what that is. But I don't know what to call it. And we tell them, we have a name for that. It's called a cat. Young children do that every day. So we develop concepts, and then we ask students, once they have understood the concept, now have a name. Where do you see this concept in life? Do you see it just in this room? No, we see it out there and over there. And, oh, I was once at my friend's house and saw this. Or I once went to the museum and saw that. Or I once went to the ocean and I saw this. And so we allow the students to contextualize, help us understand that this this phenomenon that we're looking at is in fact all around us. And then problematization. Okay, what would you like to know about this? What kind of problems can we resolve? What kind of things can we ask? What sort of answers do you want? And in so allowing students to problematize this, we are letting them, in some sense, lead the instruction. They have now set goals. These are the things we want to know about this subject matter. So you will see that as they go through this process, they have certain types of intellectual skills that they develop. So observing, conceptualizing, ordering, classifying, communicating results, and identifying problems. That's what scientists do. But this is at the lowest level. And what we find is that as we go from the lowest levels of inquiry, from discovery learning up to hypothetical explanation, the skill set, the intellectual skill set, really starts getting higher and higher and higher. Now, getting students simply to memorize physics content is not the purpose behind physics teaching, I guarantee you. Because if they cannot use this information to solve real-world problems, then what's the use of education? I'm not going to ask all students to explain hypothetically why this occurs or why that occurs in nature. But I would say to them, how do you apply your physics knowledge to determining whether or not we should build a nuclear power plant here in Sao Carlos? Should we put in a nuclear waste dump here? Should we put in wind farms here? You can use physics to answer those sorts of questions. Interactive demonstrations. Students are engaged in explanations. Why do we study physics? Well, really a couple of reasons. One is to explain. One is to predict. One is to control nature. Okay? Those are some of the good reasons. So let's start the students on that process. So let's get them to look at a demonstration, to understand what it is, to provide some sort of an explanation, or maybe make a prediction. And as students make predictions, you ask them, okay, how did you do that? Okay, this is called inductive reasoning. How did you do this reasoning? How did you draw that conclusion? And students start explaining things. And when they explain things, they make all sorts of assumptions. And sometimes they reveal, they show that they have alternative conceptions.